First generation solar cells. Hello and welcome to D Creations Resources. Earlier we have spoken about different generations of solar cells, and we have seen that basically these generations tell the story of the stages of the past evolution in the research of solar cells. Now let's talk about the first generation solar cells. This particular category includes photovoltaic cell technologies based on crystalline silicon. It could be monocrystalline, polycrystalline, multicrystalline, and also solar cells based on 3,5 semiconductors like gallium arsenide. To talk about silicon based solar cells, they of course have been the first sector of photovoltaics, and they started with raw materials supplied by the industry of microelectronics, since we know that silicon is an integral part of microelectronics. Even now, solar cells based on silicon have the largest market share, as they have the highest efficiency in comparison with other generations, and of course they have the most commonly used ones. Now, this first generation of photovoltaic cells basically has wafer based technology. It's also sometimes called as thick layer or thick film technology, and these consist of monocrystalline silicon, which have efficiency up to 24%, and of course silicon has band gap of 1.1 electron volt. The lifespan in case of first generation solar cells is very large. For example, here the lifespan is around 25 years. So there are advantages like stability, high performance, long service life. But at the same time, there are disadvantages like very high manufacturing cost or temperature sensitivity in the negative sense, because the efficiency decreases at very high temperatures. There could be problem of absorption, etc. The process to prepare these solar cells is also tedious. So of course we want to prepare a PN junction based on silicon, and usually monocrystalline silicon solar cells involve growing silicon blocks from small monocrystalline silicon seeds and then cutting them to form monocrystalline silicon wafers. So these are fabricated by a process called CZ process or Jokralski process. And monocrystalline material, it's basically widely used due to its high efficiency as compared to multicrystalline material. But there are technological challenges associated with this process, because this requires stringent requirements of material purity. Then there's high material consumption during the cell production or the cell manufacturing process, and the limited module sizes are composed of these cells. Multicrystalline silicon blocks, on the other hand, are produced through melting high purity silicon and crystallizing it in a big crucible by directional solidification process. There is no reference crystal orientation in this process, as in the CZ process, and therefore silicon material with different orientations is produced. The most commonly used base material for solar cells are p-type silicon substrates, which are doped with boron, and n-type silicon substrates. Now there are challenges such that the doping has to be uniform along the silicon block. So that is an important challenge one has to address. So in the production of crystalline solar cells, 6 or more steps need to be carried out sequentially. These typically include surface texturing, doping, diffusion, oxide removal, anti-reflective coating, metallization, and firing. At the end of this process, the cell efficiency and other parameters are measured, of course under standard test conditions. The efficiency of photovoltaic cells is determined by the material quality that is used in their manufacture. So the theoretical efficiency threshold for first generation PV cells is estimated at around 29.4%, and a sufficiently close value was reached long back, which was around 25% efficiency. But after that, there have been very minimal improvements in efficiency values that have been achieved. Now, the limit which talks about the efficiency is called Shockley queisser limit. These are names. Shockley is SHOCKLEY and queisser is QUEISSER limit. And basically, they are surnames of two people, namely William Shockley and Hans Queisser, who basically calculated this limit. And so you can say it's the calculation of the maximum theoretical efficiency of a solar cell made from a single p-n junction. And they had published a paper long back in 1961 in the Journal of Applied Physics about detailed balance limit of efficiency of p-n junction solar cells. And this limit is calculated by examining the amount of electrical energy that is extracted per incident photon. We know that photons is the input and electrons is the output. So that's why efficiency, as we know, is output per input. So here it's amount of electrical energy that is extracted per incident photon. This calculation places maximum solar conversion efficiency around 33.7%, assuming a single p-n junction with a band gap of 1.4 eV and using an AM 1.5 solar spectrum. So therefore, an ideal solar cell with incident solar radiation will generate 337 watt per meter square. When the solar radiation is modeled as 6000 K blackbody radiation, the maximum efficiency occurs when the band gap energy is EG, as it is denoted, is 1.4 eV. So the maximum efficiency of a single junction solar cell, it can be plotted as a function of band gap energy, and you can see that the peak is occurring at around 33.7% at the designated band gap of 1.4 eV. Now this is done on basis of certain primary considerations. For example, the black body radiation from solar cell at room temperature, that is 300 Kelvin, can be captured by the cell and represents about 7% of the available incoming energy. And the energy which is lost in the cell is generally turned into heat. So any inefficiency in the cell increases the cell temperature when it is placed in sunlight. And as the temperature of the cells increases, the black body radiation also increases until equilibrium is reached. So in practice, this equilibrium is normally reached at temperature as high as 360 Kelvin. And cells normally operate at lower efficiencies than their room temperature rating at such higher temperatures. Also, another primary factor is that of recombination. So this recombination places an upper limit on the rate of electron hole production. In silicon, this reduces the theoretical performance under normal operating conditions by another 10% over and above the thermal losses. Also, there can be spectrum losses. The limit for short circuit current density, that means the current density at zero voltage. This assumes that each solar photon gets converted into an electron that flows through the circuit. At higher band gaps, there are fewer photons above the band gap, and therefore the current density decreases. So this is an important consideration, the Shockley-Queisser limit, that needs to be understood when we are studying solar cells. So basically, silicon is offering several advantages. Silicon is second most abundant material on the earth, that is after oxygen, and it's providing a combination of high efficiency, long lifetime, and since it's crystalline, it basically offers an organized structure that makes conversion of light into electricity more efficient. These silicon based solar cells are very much relevant, and as said earlier, they basically are right now occupying the largest market share. So these first generation solar cells will keep on ruling for some more years at least.